Hello and welcome to Cannon County High School Algebra 2. I hope you all had a good weekend. We are going to keep going with probability, and we are going to be discussing the difference between independent events and dependent events. You now are pretty good at finding basic probabilities. You just find everything that could possibly be in the sample space, and you put that in the denominator, and then you put in the numerator all the different ways of getting that particular outcome, and you just divide them, and that's the probability. Well, there are different kind of events. There's independent events and dependent events. For instance, here's a coin. Let's say I were going to flip this coin. It has heads, it has tails, it's a quarter. What's the probability that I get heads? All right, there's heads. The probability is 1 out of 2 because there's 1 heads and there's 2 sides, so that's 1 out of 2. What if I were to flip the coin twice? All right, got heads the first time. Let's say if I flip the coin twice, I got heads twice. What's the probability that I get heads twice? Well, does the fact that I got heads the first time affect whether or not I'm going to get heads the second time? Does flipping the coin, when you flip a coin and you get heads the first time, does the coin have any memory of what just happened? It really doesn't. And so that's what we'd call an independent event. Each time you flip the coin is an independent event. Each time you get exactly the same probability. It's 1/2. Think about cards. We're going to take this small deck of cards. We only have 4 cards in this entire deck. We shuffle them up. All the cards are the ace, 2, 3, and 4 of diamonds again. Let's say I wanted us to shuffle up the deck and say, what's the probability of getting the ace of diamonds when I shuffle up the cards? So I shuffle up the cards. All right, what's the probability of getting the ace of diamonds? You would say it's 1 out of 4 because there's 4 possible outcomes, only one of which is the ace of diamonds. Let's say I choose this one. And there it is. It's the ace of diamonds. That was a 1 out of 4 possibility. Now, what if I put it back in here and shuffle it all up again? What's the probability of getting the ace of diamonds now? It's still 1 out of 4. But what if, after I chose a card, let's say I get the ace of diamonds, if you take one card away, let's say I want to choose the ace of diamonds, but I got the 3 of diamonds first. If I take that card and set it aside, what's the probability that I get the ace of diamonds this time? Well, it's different, right? Because we have a different number of cards. So that would be a dependent event. Okay? So there's a difference between independent and dependent. So Mr. Lyon, I'm going to have you sit over here again and make sure we get all this right. But I want you to, if this was class, this is where we'd take some notes, but there's really only 2 definitions that you need to know. If 2 events are independent, that means that the outcome of the first event does not affect the outcome of the second event. Kind of like when you flip a coin. When you flip a coin, you either get heads or tails. It doesn't matter on the second one what happened on the first one. In dependent events, the outcome of the first event affects the outcome of the second event. So again, let me give you another example using cards. Let's say we take all 52 cards and we shuffle them up. What's the probability that you get a black card when you choose a card at random? What's the probability that you get a black card? Well, it'd be 1/2. It'd be 26 divided by 52, which is a half. There's 26 black cards in the deck out of a possible 52. Let's say we got a black card on the first one, but we set that aside. What's the probability of getting a black card now? Well, there's no longer 26 black cards in the deck. And there's no longer 52 cards overall in the deck. The probability now would be 25 out of 51. Do you see how getting a black card a second time is a dependent event? Because the probability changed. The fact that I took this black card out of the deck changes the probability of me getting a black card next time. The probability is a little bit less. It's only 25 out of 51. It's not 26 out of 52 anymore. So that is a dependent event. So One formula that is always true of independent events is that the probability of getting A and B, so event A and event B, kind of like using our frequency tables yesterday, has to be equal to the probability of A times the probability of B. So we're not going to actually calculate today any events. All we're going to do today is figure out, are two events independent? Because if this is true, if this is true, then they do have to be independent. The probability of A and B has to equal the probability of A times the probability of B. So let's try that. We're going to be looking at CC7. We're just going to try a few of these and see how we do. All right. All they're going to be asking us basically is yes and no questions here. It says in an experiment, the probability that event A occurs 2/7. The probability that event B occurs is 2/5. And the probability that events A and B both occur are 4/35. Are A and B independent events? Well, if they are, then that means that this formula has to hold true. So really, we just have to figure out, is 2/7 times 2/5 equal to 4/35? Okay, so on paper, I'm going to write that down. 2/7 times 2/5, is that equal to 4/35? Well, you know from, what would that have been, 6th grade, 5th grade class, math class, that when you multiply the numerators. 2 times 2 is 4, 7 times 5 is 35. So I would say absolutely yes, this one is true, and therefore these are independent events. So I'm going to click yes, and I'm going to click submit, and that's it. Let's try another one. In an experiment, the probability that event A occurs is 4/5. The probability that B occurs is 7/8. Find the probability that A and B, and the probability A and B both occur is 7/10. So again, this whole section on this, we're not even calculating any of these probabilities. We'll do that later. All we really want to know is, in this case, is 4/5 times 7/8, is that equal to 7/10? Well, let's see what we can cancel out here. The 4 and the 8 cancel to a 1 and a 2. 1 times 7 is 10. 1 times 7 is 7. 5 times 2 is 10. So yeah, I think in this case, the answer again is going to be yes. Okay? So if it equals, then you say yes. If it doesn't, you say no. Let's skip up a level or two and see if these can get any more difficult. All right, well, they give us the same information, but this time they give it to us in a frequency table. Curious about people's recycling behaviors, Rebecca put on some gloves and sifted through some recycling and trash bins. She kept count of the plastic type of each bottle and which bottles are properly dispensed. So let's see. Are the events the bottle is incorrectly placed and the bottle is made of plastic number 4 independent? Okay, well, what is the probability that the bottle is incorrectly placed? Well, how many things are in the sample space here? We've got what? 4, 4, 4, and 1. That's 13. So you got incorrectly placed. That's 5 out of 13. And the bottle is made of plastic number 4. That's 8 out of 13. And what's the probability that they are both incorrectly placed and made of plastic 4? Well, that would be 4 out of 13. So let's just put those in the formula and see if they work. We said the probability that it was incorrectly placed was 5 out of 13. And the probability that it was plastic number 4 was 8 out of 13. And what was the probability that they're both true? Well, that's 4 out of 13. Well, I can already see we're going to have a problem with this, because this times this definitely does not equal that. So I'm going to say no to this one. Okay, let's try one more like that. All right, let's see here. A creative writing class compiled a list of their favorite superheroes. They listed each superhero's superpower and personality flaw. Are the events the superhero can read minds and the superhero is lazy? I don't know any superheroes that are lazy. Anyway, are they independent? Let's see here. What's the probability that a superhero can read minds? Can read minds? It would be, what? Let's see, how many in the sample space here? We've got 6 and 5, that's 11, 15. We've got 18 total. So that means, let's see, can read minds, that's 7 out of 18. I'm gonna write that on my paper before I bring it over here. 7 out of 18. Superhero is lazy. That is 8 out of 18. Okay. Can read minds and is lazy. That would be 3 out of 18. So what do you think? I would say no again, because this times this does not equal this. These don't cancel out. We're not adding. That doesn't work. Let's see. If we cancel this with this, that would give us, let's see, 4 out of 9. You could cancel this 18 with this 4 and get 2 out of 9. That would give us 4 times 2 is 14. 9 times 9 is 81. Okay, does that work out to 3/18? I don't think it does. So I'm gonna say no. No on this one. All right. So you get the idea. Let's go up one more level and do a problem. Let's see how we do here. All right. Every summer, Ernesto goes on a week-long canoe trip with his childhood camp friends. After the trip, he usually purchases some oars from the destination city. His collection of oars is organized by year and type of wood. Are the events the oar was purchased in 2012 and the oar was made of ash wood independent? Okay, what's the probability that it was purchased in 2012? Let's see, well, if we add all these up, let's see, 15 and 5 is 20, 30, 41, 50. It looks like we have 50 altogether here. So what's the probability that it was purchased in 2012? That would be 9 and 3 would be 12 out of 50. I'm gonna write that down on the paper. I'll bring it over in a second. What's the probability that it was made of ash wood? Well, that would be, let's see, 8, 10, and 3 is 21, so that's 21 out of 50. And that it was 2012 and made of ash wood would be 3 out of 50. So let's see, does that work when we plug it into the formula? Let's take a look. Let's see, well, we could divide this, we could divide each of those by 2, and that would give us 6 out of 25. Does anything else cancel? Well, so we could divide each of those by 2. That would give us 3 out of 25. Anything else cancel out here? Let's see. So is 3, do these cancel out to give you 3 over 50? No, I don't think they do. So again, if you want to use your calculator, you can. But that's it. So that's the idea. What I want you to do, just go ahead and try CC.7. And remember, all they're really asking you to do here is to use this formula. If these two are independent, then this formula has to be true. If not, then it doesn't. Okay? So this isn't really, again, kind of doing this as a building block to where we're going to use this tomorrow to actually maybe calculate some probabilities of independent and dependent events. But for today, all they're asking you to do is just check. So just take this and check it and see if it's right. Okay? Thanks for watching. We'll talk to you later. Bye.